Hi, everyone. Here are the notes for 12.4. Today, we will be talking about normal distributions like a bell curve, understanding the 68, 95, 99.7 rule, finding scores at standard deviation, using that rule, finding a z-score, understanding percentiles and quartiles, use and interpret margins of errors, and recognize distributions that are not normal. Okay, so a lot to get through in 12.4, but not to worry. So it starts off talking about adult heights. The mean height in 1 million BC, I don't even know how they know that, was 4 feet 6 inches, so very small. Can you imagine like everybody in Colorado being 4 feet 6 inches tall? It's like everybody's in elementary school. The mean height for women was 4 feet 2 inches tall, so small. Because of improved diets and medical care, the mean height for men is now 5 feet 10 inches tall, so more than a foot taller. And for women is 5'5". Mean adult heights are expected to plateau by 2050. So we're looking here. This first histogram has height and the number of men. Then our sample size gets bigger, but still a similar kind of shape. Then our sample size increases even more, and it gets to be more like a bell curve, and then even more. And there's our traditional bell curve. So kind of like when we were doing probability, like the more times you flip the coin, the closer you're going to get to theoretical probability. If you guys are going to move on to taking calculus in college, these are the types of things you're going to be looking at, as area under curves and understanding that you can break a curve down into smaller pieces like this. Okay, that's one of the big pieces of calculus. All right, so the standard deviation and z-score. So we just talked about standard deviation in the last video, 12.3. And here you can actually see that standard deviation. So remember, the standard deviation was the average distance to the mean. So in a normal curve, your mean is going to be 0 here, and your standard deviation is going to be this distance here. Okay, so there's one standard deviation. That's why it's +1. So one standard deviation greater than the mean. Then we can add another standard deviation greater than the mean, and then a third. And we also go backwards, so we have a -1 standard deviation. It's just that distance, okay? And then here's this rule. And if you remember this rule, you can answer a lot of questions. What this rule says is approximately 68% of the data fall within one standard deviation of the mean in both directions. So let me preface this by, let's pretend that these are your SAT scores. This makes the most sense a lot of times to high school students. So let's pretend this is a curve that represents all of the SAT scores for students across the United States. So everybody on this side are going to be feeling pretty good about their score. The farther you get, the better your score is. Everybody on this side is maybe not going to be feeling as good about their score. But let's say that this is all of the students in the United States. I'm not sure off the top of my head how many students take it, but 68%, so 18% more than half, all of their scores are going to fall within this area right here, okay? The other thing we need to realize is that the area, just because it is probability, a curve is just probability, like the probability of somebody's score falling in this yellow area is 68%. The whole curve represents 100%, okay? Just like we're talking about probability. So this whole curve, the area under the curve represents 100%. And the yellow area that I just colored in is 68%. So you can see here at the top how they said between those two scores is 68%. But then it also says that if you go out one more, so let's say we take that yellow and then we add in the next standard deviation. So I'll color in this little piece green. Okay, and here. So the yellow part represents 68%. The yellow and the green part represents 95%. So 95% of the students who take this test will fall between -2 standard deviations and +2 standard deviations. And then finally, this rule says that 99.7, so almost all, 99.7 of students will fall in between +3 and -3. So the 99.7 is all of the yellow, all of the green, and all of the blue. Okay. The 95% is just the yellow and the green, and the 68% is just the yellow. Okay. So mark this. This is page 809, and it has our rule. 68, 95, 99.7 rule. The name of it pretty much says it all. If you can remember the name, you're good to go. All right. So we can use that information here. So this says male adult heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. So below, that's what we have. Our mean goes in the middle. That's 70 inches. How many? That's just below 6 feet, right? 6 feet would be 72 inches. And then our standard deviation is 4 inches, which means when we go up, 70 plus 4 is 74. That's one standard deviation. 74 plus another standard deviation of 4 is 78. 78 plus 4 is 82. So that's how they got those numbers down there. 74 is plus 1 standard deviation. 78 is plus 2 standard deviations. And 82 is plus 3 standard deviations. Then we go the other direction, we subtract 4. So 70 inches minus 4 inches is 66 inches. 66 inches minus 4 inches is 62 inches. And then 62 inches minus another 4 inches is 58 inches. Okay, so now we have +1. So 70 is 0. That's our mean. 74 is plus 1 standard deviation. 78 is plus 2 standard deviations. And 82 is plus 3 standard deviations. 66 is minus 1 standard deviation. 62 is minus 2 standard deviations. And 58 is minus 3 standard deviations. These numbers down here are going to be my standard score. And these numbers here, or my standard height, and these numbers here are the actual heights. Okay. So this question says, find the height that is 2 standard deviations above the mean. Well, we did that. That was 78. Okay. And 3 standard deviations below the mean was 58. And I just did it by marking up the graph. They did it by math. If you want to see how they did it, simply read through the solution. Sorry, you guys have like a stuffy nose. All right, so use the distribution of male adult heights on the previous page to find the percentage of men in North America with heights between 66 and 74. So that means, and they did it right here, 66 is -1 standard deviation, 74 is +1, and that's part of that rule. That means 68% fall within those two. Between 70 and 74 means, so this is interesting. Between 70 and 74 would be half of that 68, right? So that's just going to be, where did they put their answer here? 34%. okay, because we just simply took half of that 68. Because this curve is symmetrical, we can say that. And then C is a little bit trickier. C says we're looking above 78. So 78 is plus 2. So we want everything above plus 2. So here's how I would do it. We know that all of this is 95%. All of this here is 95%. So that means everything below and everything above is going to be 5% to equal that 100%, right? But if we only want what's above, we want half of that 5%. Okay, so that means everything above 78 is going to be 2.5%. Okay. So checkpoint 2, use the distribution of male adult heights in North America to find the percentage of men with heights between 62 and 78. That's easy. That's right here, 95%, right? Look at that. Between 70 and 78, well, that's going to be half of 95. That's going to be right here. It's going to be half of 95. And above 74. So 74, we're going to do kind of just like we did. Between 74 and 66 is going to be 68. That means that everything above and everything below has to be 32. And we only want half of that, so we want half of 32, which would be 16%. All right, this says because normal distribution of male adult height in North America has a mean of 70 inches, a standard deviation of 4 inches. Blah, blah, blah. In a normal distribution, a z-score, which means standard score is what I was talking about, describes how many standard deviations a particular data item lies above or below the mean. Okay, so what it's saying in this sentence is, if we go back and look, let's go back to the original actual one here. Those standard deviations, and I already said this right here, these numbers are the standard scores. So this is what I was talking about. The standard score in this distribution of 70 is 0. The standard score of 74 is +1. The standard score of 66 is -1. Okay. Z-score, you'll also hear it called the Z-score. And here's the formula for how to compute the Z-scores. The Z-score is equal to whatever your data item minus the mean divided by the standard deviation. So up here, it says that a height of 78 inches is 2 standard deviations. So let's see if that's true. Our data item, that is the 78, minus 70 is our mean, divided by our standard deviation, which is 4, and we get 8 divided by 4, which is +2. Okay, and here they're doing this. They are saying, and I can just draw this for you really quickly. If we have a normal distribution of baby weights, and it says the mean always goes in the middle. It says the mean is 7 pounds, and the standard deviation is 0.8 of a pound. So we're going to start with 7, and then we're going to go +1 is going to be 7.8. 2 is going to be 8.7. 8.6. And 3 is going to be 9.4. I'm doing this in my head. Tell me if I get it wrong. And let's do every other. So start with 7, then 7.8, then 8.6. It's a little bit easier to read. And then backwards, if that's 7, this is going to be 6.2. And then 5.4. And then I have to use my calculator. I don't want to mess this up. So 7 minus 0.8 minus 0.8 minus 0.8. Oops. $4.6. Okay, so this is 0 plus 1 plus 2 plus 3 minus 1 minus 2 minus 3. So these are the standard scores. These are the actual weights. Find the z-score for weight of 9 pounds. So 9 pounds is going to be, if it was just 8.6, we could say it was plus 2. If it was 9.4, we could say it's plus 3. But since it's in between those two weights, we have to use our formula. So the z-score is going to be equal to, and it wants 9 is what we want to know, minus 7 is our mean, divided by 0.8. It's going to be equal to 2 divided by 0.8, which is 2.5. So it actually was right in the middle. Okay. All right, and then it does it for 7. Well, 7, you didn't even need to do what it did here because we can see from our picture it was exactly, it was the mean, so we know it was 0. And for 6, they had to put it back into the formula. Okay, so this time, oh, so this was it, did it for us. Checkpoint 3 says the length of horse, oh, so this is different. The length of horse pregnancies from conception to birth is normally distributed with a mean of 366 days and a standard deviation of 3 days. Find the z-score. I'll do the first one for you, and then you just put in the other days. So our z is equal to our data. So we're going to start off with 342 minus the mean, 336 divided by 3, because that's a standard deviation. So it would be positive 2. Then to do the other ones, you just replace this number and that's it. All right, interpreting z-scores. A student scores 70 on an arithmetic test and 66 on a vocabulary test. The scores for both tests are normally distributed. The arithmetic test has a mean of 60 and a standard deviation of 20. The vocab test has a mean of 60 and a standard deviation of 2. On which test did the student have a better score? So in order to compare them, you have to find the standard score. So they find the standard score for the arithmetic test. So they take the score they got, 70, minus the mean, which was 60, divided by the standard deviation, which was 20, and they got 0.5. Then for the vocab test, the student scored a 66, the mean was 60, and the standard deviation was 2. The student got a positive 3. So they did way better on the vocab test than they did on the math test, arithmetic. I don't know why I'm having a hard time pronouncing that. All right, checkpoint 4. The Scholastic Aptitude SAT has a mean of 500 and a standard deviation of 100. That's pretty standard. The ACT has a mean of 18 and a standard deviation of 6. Suppose that you score 550 on the SAT and a 24 on the ACT. So we need to find the z-scores. So if we do it for the SAT, I'll just get it set up for you. The mean, we're going to subtract. The mean is 500 and the standard deviation was 100. And then this is where you put your score. And then for the ACT, your score minus the mean this time is 18 divided by the standard deviation, which is 6. So whichever number is higher is the test you did better on. All right, IQs, understanding the z-score. What is the IQ corresponding to a z-score of? Oh, so we're just going backwards, you guys. So check it. Up here, we were solving for z, and down here, you're solving for your actual score. So if you, this time, our z is equal to negative 1.5, which is equal to our x, what we want to find, minus the mean, which it says is 100, divided by the standard deviation, which is 16. And you can find all of these numbers in the question. So this time, we need to do 16 times negative 1.5, which is going to be negative 24, is equal to x minus 100. So you're going to add 100 to both sides, and we get x is equal to 76. So if you got a score of 76 on the IQ, you would be negative, you would have a standard score of negative 1.5. And then it says Mensa is a group of people with high IQs whose members have a z-score of 2.05 or higher. What is the IQs corresponding to 2.05 or higher? So we're just going to do the same thing, but this time we're going to put 2.05 equals x minus 100 divided by 16. So 2.05 times 16 is 32.8. I'm just cross multiplying here. Equals x minus 100, and then we need to add 100 to both sides. So this time your score would be 132.8. Okay, so checkpoint 5, I'll get you started. So we're using the same IQ scores. This time we want to know for A, if your score is negative 2.25, then what is your actual IQ number? And if your score is 1.75, same thing, what is your, that's a 16. So solve these. Feel free to use your calculator, Google, however you want to do that math. Percentiles and quartiles. A z-score measures a data item's position in a normal distribution. Another measure of a data's item is its percentile. Percentiles are often associated with scores on standardized tests, or like if you have a baby brother or sister, you go in to the doctor like, oh, they're in the 95th percentile of height, which means they're really tall, right? It means they are above 95% of everybody else. Here they're talking about if your score is in the 45th percentile, that means that you were only above 45% of the scores. And if you're in the 95th percentile, it means you're above 95% of the scores. Okay. If n% of the items in a distribution are less than a particular data item, we say that that item is in the nth percentile. Okay. Example 6, the cutoff IQ score for Mensa membership, 132.8, I think we just found that, is in the 98th percentile. Oh, are you okay, puppy? The 98th percentile. What does this mean? It means that your score is above 98% of all other scores. A student scored in the 75th percentile. What does this mean? It means that they scored above 75% of all the students. Loopholes and margins of error. Interesting. Interesting because today is election day. 3 commonly encountered percentiles are quartiles. The quartiles divide data sets into 4 equal parts. The 25th percentile is the first quartile. The 50th percentile is the second quartile. The 75th percentile is the third quartile. So here, what activities do you dread? And it gives us some percents here. If you look at the results of a poll, like the one shown in figure 12.18, you will observe that a margin of error is reported. Surveys and opinion polls often give a margin of error. Let's use our understanding of the normal distribution to see how to calculate and interpret margins of errors. Suppose that P% of the population of adults dread public speaking. Instead of taking only one random sample of 1,000 adults, we repeat the process of selecting a random sample of 1,000 adults hundreds of times. So we do it a bunch of times. Then we calculate the percentage of adults for each sample who dread public speaking. With random sampling, we expect to find the percentage in many of the samples close to that percent, with relatively few examples having percentages far from that same number. That number was, where's that? 46%. Okay, so we are thinking that most things are going to be close to that 46%. Okay, so P is 46%. Okay, so all of those samples should be really close to 46%. Figure 12.9 shows that the percentage of US adults don't matter by normal distribution. The mean of this distribution is the actual population percent, which is 46%, and is the most frequent result from the sample. So that's interesting. So something you need to realize about normal curves is that the mean and the median are the same. This is the only time that ever happens, is with a normal curve. And also the mode, because it literally just said that's the most often that it occurs. Okay. Mathematicians have shown that the standard deviation of a normal distribution is approximately 1 divided by 2 times the square root of n, where n is the sample size times 100%. Okay, and we're just going to use this rule that we just saw and learned. Says that approximately 95% of the samples have a percentage within 2 standard deviations of what we're talking about, that 46%. Okay. So when they do all of this math, they call that the margin of error. And when reduced down, the margin of error is plus or minus that. So if you're looking at this percent up here, your margin of error would be plus or minus that. Using an interpreting margin of error. So we're looking at this table, which is the same as that bar graph we looked at. Verify the margin of error that was given for this survey. So we're just using this formula right here that it boiled down to. And the n is the number of samples, okay? The number of people. The sample size, which in this case is 1,000. So what they said was the margin of error is plus or minus 1 divided by the square root of 1,000 times 100%, which is approximately plus or minus 0.032 times 100%, which is plus or minus 3.2%. They did the same for part B. Oh, this time they solved. The sample percent was 46%. I didn't read the question, I'm sorry. Write a statement about percentage of adults in the US population who dread public speaking. Okay, and what they said was the sample percent, we can be 95% confident. Oh, we're doing a confidence statement. We can be 95% confident that between 42.8% and 49.2%, because all they did is they took this 3.2% and they subtracted it from the mean, and they also added it to the mean. And that gives us our 95% confidence level. So we are 95% confidence that between 42.8% and 49.2% of all adults dread public speaking. Okay, so checkpoint 7. Checkpoint 7, we first wants us to find the margin of error for this. So I'm just trying to see how many people took this poll so that I can put it into the equation. Let me pause for you guys so you don't have to watch me do that. Oh, you guys, I must be tireder than I thought. I was just staring at this page forever before I read down here that it gave us the number. Okay, so now we can find the margin of error because we just used that formula from the page before, which is 1 over the square root of 2,513, and then times 100%. So if we put that in the calculadora, we get approximately 2%, which means we are 95% confident that the number of books US adults read per year is between and then where is our mean? We're going to have to find our mean. 36, 13, 36 plus 13. Plus 90. Oh, it wants, sorry, you guys. Eternal asked this question about more than 10 books. Whoops, more than 10 books per year. More than 10 books was 36%. So we are 95% confident that the number of books that the number of books US adults read per year is greater than 10 lies between 34% and 38%. Okay, so what we did was we took this 36% because it wanted to know greater than 10%. I don't know why it didn't give us a mean after that's what they just showed you. And we're gonna add that 2%, and that's where we get the 38%. And we're gonna subtract that 2%, and that's where we get the 34%. All right, you guys.